Okay, I guess we're ready to begin. So, good morning, everyone. I'm Nitin Samarth. I'm a professor of physics in the Abhinav College of Science, and I'm also a professor of material science and engineering. So it's an honor and privilege to welcome you here to the fourth lecture in the 2025 series of the Ashtekar Frontiers of Science lecture series. So as you probably already know, this is a very popular public winter lecture series, and it's in its 31st year. So let me just make some comments first about the series itself. The series was founded by Ashtekar shortly after he arrived here at Penn State. And he started this series in 1995. Abhay came here to start a new research center that has now become an internationally renowned institute for gravitation and the cosmos. It's a mecca for people working in that field from all across the world. And this lecture series, which has been extremely popular and active, was really shepherded along and successful because of the tireless efforts of Barbara Kennedy, who gave it a lot of tender love and attention, and took care of this series for 25 years. And she really made it one of the most successful science outreach events, in central Pennsylvania. So I mentioned Abhay Ashtekar. He's just arriving. Thanks, Abhay, for starting this series, which has really made a big impact here. So this year, as you can see from the earlier slide, or maybe it's the next slide, I forget, but this year celebrates 100 years of quantum science. And in recognition of this centennial, UNESCO has designated 2025 as the International Year of Quantum Science and Quantum Science and Technology. So all around the world, academic institutions like Penn State, scientific societies like the American Physical Society or the APS have been organizing events to try to promulgate, the awareness of quantum science and its impact on the world and so on. And this lecture series, which is titled 2025 Year of the Quantum, plays an important role in this context through talks that explore how physics at the smallest length scales affects our understanding of the world, but also our daily lives. So as you'll see through these talks, quantum science and technology has impacted the way we might carry out new kinds of computation. It'll impact how we communicate, how we send secure information from one place to another. And some of this is already happening at the lab scale, right? And at some stage, it is going to impact our lives. Now, some of you in the audience know this, but many of you may not. Okay, many of you may not actually be aware of the fact that quantum science and technology already plays an important role in your lives. And this is because of what many of us like to call the first quantum revolution. So, every time you ask Siri to show you directions to some, place that you're going to, you rely on GPS, and GPS relies on atomic clocks. So the quantum mechanics of atomic clocks, the accuracy of keeping time with those atomic clocks allows you to get where you want to go. Every time that you download one of your family videos that's stored, let's say, on a server somewhere on the cloud, the way that information, the way that data is read is by using a quantum mechanical process called quantum tunneling. And it's purely quantum mechanical. And every time you switch on one of these magnificent displays that you get at Best Buys, not all of them, but some of them, which are called QLED displays, the light, the pixels that generate the images, those pixels rely on a concept called quantum confinement, which occurs in materials, quantum materials called quantum dots. So, this aspect of quantum science and technology has already crept into our lives. there hasn't been that much hoopla about it. So you might wonder, why is it that every now and then, I see some story in the New York Times or someplace, making a big fuss about some enormous advance in quantum technology. Well, the reason for this is because this first quantum revolution was relatively easy. The time scale or the period from conceiving, some kind of explicitly quantum technology to its manufacturing translation occurred within maybe a decade or so. But now we're in the midst of a second, what some of us like to call the second quantum revolution. So here we're now trying to use all aspects of the quantum mechanical wave function. We're looking at concepts called entanglement and coherence. And because of this, it's a much, much bigger challenge. And you do see a fuss made about this because every incremental advance that we make in the lab in a university or in a company like Microsoft, you might have seen something in the news in the last few days, IBM, Google, and so on, every small incremental step we make forward, could potentially have an enormous impact. Not immediately, but once we make that translation from the lab to an actual technology that impacts all of us. When that's going to happen, I think there are a variety of opinions on this. Maybe we'll ask today's speaker about that. But it's really an interesting stage of this quantum revolution. And because of that, Penn State has made investments in this field. So if you look at colleges across Penn State, College of Science, College of Engineering, IST, Earth and Mineral Sciences, we've been recruiting faculty who work at, in fields of quantum materials, quantum computing, quantum algorithms, and so on, and trying to push this field forward, pushing the frontiers of this field forward. And we've been lucky enough to attract some leaders in the field at Penn State. And I hope that we're going to keep making investments in this field so that Penn State can be at the leading edge of this really rapidly evolving area. And it's very exciting. The challenges are immense, but that's what makes it so exciting, right? So today's lecture topic, Accurate Quantum Computing, is being presented by Abhinav Kandala, an experimental physicist and a principal research scientist at IBM. Now, as you'll learn in a few minutes, I happen to know Abhinav extremely well, but I still have to read something here because I don't know everything he's been doing recently. So Abhinav currently leads the quantum capabilities and demonstrations team at IBM, building the tools for executing large quantum circuits and exploring beyond classical quantum computation. His work at IBM has spanned the control and coherence of superconducting qubits, multi-qubit characterization, and the deployment and applications of quantum computers. Now, his most significant contributions have been towards exploring whether the current platforms for quantum computing, which are really, as you will learn from him briefly, are quite noisy. They're imperfect, they're noisy, they're not things that we can use for, for major purposes. But can you actually do something useful with them? And he's shown that you actually can. So in 2023, he led the quantum utility experiment at IBM. So Abhinav received his bachelor's in engineering physics at IIT Bombay in 2008. That happens to be my alma mater also when I was an undergraduate in India. He then came to Penn State to do his PhD, and I was very lucky to attract him to my lab. So I had the pleasure of having him as a graduate student while he was at Penn State. He graduated from here with a PhD in 2015. His PhD work had nothing absolutely to do with quantum computing. We didn't pursue qubits or anything of the sort. We were studying quantum materials, and he carried out some very interesting research on a quantum material known as the quantum anomalous Hall insulator. So after graduating from here, he went to IBM as a postdoc, and his first paper as a postdoc appeared on the cover of a prominent journal called Nature. And then he became a staff scientist at IBM, and he's been pushing the field forward over there. So Abhinav has received 2 important honors. He, let's see, in 2019, he received the MIT Tech Review 35 Innovators Under 35 Award. And very recently, just last year in 2024, his alma mater, IIT Bombay, gave him the Young Alumni Achiever Award. Following the lecture, graduate student, one of the graduate students in physics, Pang Du, who is at the back, will lead a moderated question and answer session with Abhinav. You should have received a paper and pen. So please, when you arrived, so please write down your questions. And our student volunteers, we don't have student volunteers today. We have, because they're all at the thon. Heather has kindly agreed to run around these stairs and collect your questions. So please do write down your questions, and I'm sure Abhinav will be very interested in answering them. So I think without further ado, then let me welcome Abhinav.
Am I audible in the back of the room? Yes. Okay, wonderful. Thank you so much for being here. I know there are more entertaining events going on campus, and I really appreciate your presence. And it also, I just came to realize it never gets any less embarrassing to have your advisor speak about you. Yeah. So today I'm going to be telling you about some newer computers, which, as Professor Samarth just mentioned, are extremely error-prone. They're very noisy. And I'm going to try and walk you through how, even despite a lot of this noise, one could hope to do accurate computations with these kinds of devices. Okay? But before I dive into the science, this is the first time since graduation that I'm physically here doing a talk. And it's really made me reminisce about my 7 years in Happy Valley. I think this was the picture on the left, I think, is from 2008 in Professor Samarth's house. We were doing a farewell party for one of the postdocs. If you know the family, the kids have really grown up. And then 7 years later, several pounds heavier. I was graduating in 2015. And these were really 7 wonderful years in Happy Valley. And the 7th year was interesting. Later I would joke about being a tenured graduate student. But no, I think I learned a lot. And I was, as I was trying to fish through emails and older presentations, I was trying to just, I was looking back at a lot of the cool devices I got to build during my time here, leveraging a lot of the amazing facilities we have in the Materials Research Institute, previously at Innovation Park and now in the Millennium Science Complex, and really having the opportunity to measure these at low temperatures in our labs in the basements of Osmond and Davy. And this was really amazing. And so as I look back, a lot of these skills continue to be very relevant to the kind of work I do today, even though it's in a slightly different field. And so I really have a lot of gratitude towards my advisor, towards the department, towards the university for all of these amazing facilities and opportunities I had here, which have led, which have enabled me to do the work I'll be talking about today. Okay. So I'm going to talk about quantum computers. Perhaps many of you have heard about this already. Presumably you've heard that this computer could do things that regular computers cannot. But maybe a more fundamental question, why do we even need faster computers? This used to be a question that I used to ask myself, even while growing up, when I used to keep hearing about the next iteration of a Pentium processor. The tasks I was doing, maybe sending, receiving emails, or receiving messages from my friends, playing computer games, there wasn't any discernible change, really, as I went from one processor family to the next. Perhaps the speed of rebooting was a little better, but on a day-to-day kind of use, there wasn't a dramatic change in what I wanted to do. It seemed perfectly fine that I could write emails and browse the internet at the speed that I was at that point in time. But of course, if I look back now, if we didn't have, as a civilization, almost this maniacal obsession of building faster and faster, more powerful computational tools, even before we knew what we could do with them, we probably wouldn't have the kind of technologies we have today, right? The smartphones, what we can do on ChatGPT. A lot of these are enabled today because we just kept building before we knew what we could do with them. So I'm definitely a huge believer in, build it and they will come, right? We want to build more powerful computational tools, and as a civilization, we're incredibly smart people to figure out amazing things that we can do with these that we couldn't do before, right? So one of these very challenging problems that requires a lot of computational resources is the estimation of the dissociation energy of a molecule. Okay? And this is a kind of curve I'll keep coming back to again and again in my talk. Okay, so let's consider a very simple example of a molecule with just 2 atoms. If you bring these atoms too close to each other, you're in this unstable state where they have a very high energy. If you completely separate them apart, there is no interaction and you have a lower energy. That's in a state of dissociation. But there'll be a state of lowest energy when they're at the perfect distance. And this is called the equilibrium state. Okay? So the energy to take a molecule from its equilibrium state and break it to dissociation, that energy is called the dissociation energy. Okay? And having an accurate measure of this is going to be very important because this enables you to accurately estimate chemical reaction rates. Okay? And this, as you can imagine, is relevant to a host of industries, a host of applications. Okay? So you want to really accurately estimate this dissociation energy because these chemical reaction rates are exponentially sensitive to that. Okay, so how does one calculate this? Okay. This will be one of the few equations I'll show, but essentially you start by expressing what's called the Hamiltonian for the system. So you express an equation which has a term for the kinetic energy of the electrons in the molecule, and then something that captures the Coulomb interactions between pairs of electrons and pairs of electrons in nuclei. Okay? And then once you express this Hamiltonian, it typically comes down to an eigenvalue problem, which basically means that you want to know what the energies are for this Hamiltonian. Okay? So there's a matrix representation for this. And essentially the task comes down to trying to diagonalize this matrix. Okay? Now, the big challenge here is the size of this matrix blows up exponentially with the number of spins or the number of electronic orbitals that one has to account for. Okay? That is a matrix of dimension 2 to the n times 2 to the n. So 2 to the n rows and 2 to the n columns. If you begin to get to a scale of about 55 to 60 spin orbitals, right, you already run out of memory on the most powerful supercomputers in the US. Right? So on Oak Ridge's Summit supercomputer, if you had to store all of this information, you would run out of memory. Okay. So doing what's called a brute force diagonalization of a matrix of this kind is an incredibly challenging task. Okay. And even in the early days of quantum mechanics, this was recognized to be a problem. Okay. And there's a very famous quote by Dirac. The underlying physical laws necessary for the mathematical theory of a large part of physics are completely known, but the difficulty is only that the exact application of these laws leads to equations that are much too complicated to be soluble. It therefore becomes desirable that approximate practical methods are developed. So basically, once you're at these scales where you can't do brute force diagonalization, where you can't access what the exact answer is, you have to develop practical, more practical, approximate classical methods that scale. Okay? And this is basically what's enabled, for instance, the field of quantum chemistry that addresses the kind of problems I was talking about, trying to estimate the dissociation energy of a molecular system. Okay? So, just a question now, right? That's worth thinking about is if you don't know what the right answer is, and you want to develop an approximate classical method, how do you even know that that approximate method is giving you something meaningful? How do you build trust in approximate methods in the absence of knowing what the right answer is? Okay? So we can think through that a little bit. Perhaps one thing to do is, well, you don't immediately start testing the method out at very large scales. Maybe you start out at a smaller scale where you can do this kind of matrix diagonalization, and you compare these approximate methods at that point. Some problems might have interesting properties, some interesting symmetries, where you know the analytical solution, even though the problem scale is much larger beyond this brute force diagonalization. Maybe at that scale you can compare. Okay. Perhaps there exist other well-established, trustworthy classical approximation methods, and when you develop something new, maybe you can compare to the accuracy of those. Right? Perhaps you could systematically change some approximation parameter that systematically increases the computational resource required, right? And you can look for convergence. You can see if you converge towards the right answer as you systematically increase some computational resource. Okay. The challenge, though, is these are approximations, and you have to work in this very uncomfortable place of not knowing exactly what the right answer is, and yet trying to build trust in these methods. So this didn't sit well with Feynman, right? And this is a very iconic and cliched quote, but this was the basic idea that if we're trying to simulate quantum mechanics on a classical computer, this is going to be hard. And to actually simulate quantum systems, one needs to build another device which also follows quantum mechanics that you can control and manipulate. Okay? So this was kind of the idea. You want to simulate the molecule on the left, and perhaps you want to build something that behaves like that molecule, which you can control and program in a very precise fashion, like the chip on the right. So for instance, if you wanted to simulate the properties of some of these molecules, you want to map these atoms onto the kind of artificial atoms I'll talk about very soon on one of these superconducting quantum processes. Right, okay. So that was one of the big motivations to build a quantum computer, to simulate other quantum systems that might be very hard to simulate otherwise with approximate classical methods or even with brute force diagonalization. Okay? So this is going to be my 2-minute crash course into quantum computing for you. So typically in our standard computers, we're very familiar with the idea of a bit. This is what we define our fundamental piece of logic with. You have a 0 and a 1, right? And then when we think of a quantum bit or a qubit, we look at states beyond just that 0 and 1. And we often represent the states of this qubit as points on a sphere, where the North Pole and the South Pole represent the 0 and the 1. But then you can also have what are called superpositions of 0 and 1, or combinations of 0 and 1. Right? So you have a certain fraction that's in 0 and a certain fraction of the state that's in 1. And now computations with this qubit are done by essentially performing rotations on this sphere. Okay? So when we talk of programming a quantum bit, what we mean is we want to perform rotations on the sphere and go from one state on the sphere to another. Okay? Now, expanding this idea to many qubits on a larger quantum processor essentially comes down to performing rotations on a much larger dimensional space. Okay? One I can't visualize on a slide like this, but that's essentially what it comes down to. And the nice thing is all of these rotations can be performed by single qubit rotations on single qubits, and then operations on pairs of qubits. And these operations on pairs of qubits are called entangling gates or entangling operations. Okay? So with so if you look at the image on the right, essentially the sequence of gates, the sequence of instructions is what one uses to perform these rotations in this larger dimensional space. And this is essentially what we're doing with quantum computing. Okay? And that series of instructions, that series of gates, that's what's called a quantum circuit. And you'll hear me use this phrase several times over the course of this talk. Okay. So now to begin to build a quantum computer, what you primarily need is a quantum mechanical two-level system, one where you have a precise computational 0 and a computational 1, and then where you can do these rotations where you're in part 0 and in part 1. And there are many different flavors of these, and you might hear about some of these in the news. Some of these you can see in the basement of Davy, in Professor Dave Weiss's lab. The platform I'm going to be talking about today are the ones that we undertake at IBM, called superconducting qubits. And these are basically circuits, very much like the kind of circuits we're familiar with for CMOS technology, but they have these interesting materials that have superconducting properties. Okay. And the fundamental building block here is basically what's called a Josephson junction. This is basically a sandwich of an insulator between two superconductors. Okay, so you have sorry. Right. So right there at that junction, you have the sandwich of an insulator that you see in the middle here, right between these two superconductors, which is aluminum oxide sandwiched between two layers of superconducting aluminum. And these are the kind of devices one can, for instance, make in the Millennium Science Complex, in our clean room, right? The very nice aspect here is, though, by circuit design, by choosing parameters for your circuit, you can essentially engineer artificial atoms. You can create macroscopic quantum objects, which now have these quantized energy levels, which one can use for the computational 0 and the computational 1. And then you can shine light on these, you can shine microwave light on these, depending on what this frequency is, to manipulate states between the computational 0 and 1. Okay? So depending on your choice of these circuit parameters, depending on your circuit design, those numbers turn out to be about 5 gigahertz. Okay. And this is quite convenient because it means that you can go, and purchase electronics that are fairly standard off the shelf to be able to shine microwave light on these systems and manipulate these quantum states. Okay. For the physicists in the room, if you wanted to translate that frequency to a temperature scale, 5 gigahertz typically corresponds to about 250 millikelvin. Which means that you have to be able to operate these devices at very, very low temperatures so that you have a well-initialized 0 state. You don't want the temperature to heat up the quantum bit and create some uncontrolled superposition of zeros and ones. Okay. So that's an example of one quantum bit, and eventually we want to build networks of these. We want to be able to perform operations on individual qubits, and we also want to entangle these together. Okay? So this is now the second piece of building a much larger quantum computer. This is an example of just a 2-qubit device, where you have one quantum bit here, you have some lines that enable you to control this quantum bit and measure the state of the bit. Here is another quantum bit, and now we want to also entangle these. And so we have what's called a coplanar waveguide resonator coupling these two. So this is basically, the next level building block of a larger quantum processor. Okay, so what's the challenge? We started out talking about how these are tremendously noisy and extremely error prone. Why is it so hard to build a quantum computer? We spoke about bits in regular classical computers. If you want to compare the errors happen even on regular classical computers. But if you want to compare the error rates, we're talking about a difference of about 23 orders of magnitude between where we are with classical computers today and quantum computers today. So if the errors are that dramatic, so much faster, can you actually even hope to do something useful with these? Right? So why are these errors even happening? What are these kinds of errors? So in that sphere representation, I showed you that the north and the south pole represent the computational 0 and the 1. Here, what happens is if you prepared, for instance, your computational 1 state, it doesn't indefinitely live in that state. In a very short amount of time, with our technology on the order of, say, about 100 microseconds, okay, it decays into the computational 0. And this is just one example of error. There are many more kinds of errors that we have to deal with, okay? But this is a challenge because these quantum bits are extremely sensitive to their environment. They're extremely sensitive to perturbations, thermal perturbations, vibrational perturbations, and a whole class of things that make you lose this computational state very easily. So this was also known very early on that this was going to be a problem. And since then, we've had a theory of quantum error correction, which is going to be the long-term solution. Okay. So I want to talk, give you a feel for what quantum error correction is and how this works, and show you that there is actually a path, even with these kinds of error rates, to build a fault-tolerant, error-corrected quantum computer. And this is something we're hoping to do at IBM very soon. So before I get into quantum error correction, it helps to actually describe how classical error correction works. Okay? So imagine you had two physical bits, right? 0 and a 1, and there's a finite probability of an error. So your 0 can flip to a 1, your 1 can flip to a 0. Okay? And that's going to be an error. How can you build some robustness against these kinds of errors? The simple principle is the idea of redundancy. We're simply going to make a certain number of copies of those physical bits. So in this case, let's say we build 7 physical bits. All right? And now each of these physical bits also have the same probability of error. Okay? That some of the zeros can flip to ones. In this case, we have 2 flips. Now what we do is we take a simple majority vote. You say that, well, out of the 7, we still have more zeros, so that must continue to be a 0, and we can correct for the flipped bits. And in the 1, we have more 1s. And now you can correct those errors and say that you have what's called a logical 1 bit. Okay? So just by the simple idea of redundancy, by encoding your information in multiple copies, and then doing something like a majority vote, you're able to potentially have something that's more robust. Of course, there are going to be examples and scenarios where this kind of code fails, right? Someone could have asked me, oh, well, you very conveniently chose the example of just 2 bits flipping. What happened if 4 bits flipped, right? The majority vote would have been wrong there. And yes, that's absolutely true. And that would be an example where this kind of encoding and decoding would fail, right? So you can define now what's called a logical error rate, right? So what is the probability of this entire kind of scheme failing, right? And the goal is to have the logical error rate to be lesser than the original error rate that you had for the individual bits to flip, right? And that will happen if that p-value, that probability of a bit flip, is sufficiently small. Okay? So this is routinely used in our hard disks, in our CDs, and so on, this kind of classical error correction. Now, many of these ideas directly translate to quantum error correction, but there are some fundamental nitty-gritties of quantum mechanics that come in the way. One is that you can't copy an arbitrary quantum state. Okay? So you can't simply take this kind of superposition state of 0 and 1 and just make multiple copies of it if you didn't know what alpha and beta were. Right? So you have to actually encode it slightly differently. That leads to preparing a fairly entangled state the way I've expressed it here. Next, how do you detect errors? Right? If you had to detect the errors, the one thing to do would be to simply measure the qubit. But then projective measurement basically leads to the collapse of the state, for those of you familiar with quantum mechanics. And that's going to basically end the computation right there. Okay? So what you have to now do is you have to introduce additional ancillary bits and entangle what are called your data qubits, the qubits you're interested in, with those, and then measure those additional qubits so you can indirectly infer what the state of the qubit, what the state of the data qubits were, the ones you were interested in. Okay? So to really simplify a lot of this, essentially what this comes down to is if you want to encode information and you want to detect errors and correct for them, you basically need to build some redundancy. You need to be able to spread your information over many, many physical qubits. You need to build lattices of large numbers of qubits, and then use these to spread out your information, like we saw in the example of the classical error correction code, and then use these to also detect and correct for errors. And this is going to be, an incredibly, incredibly challenging task for us as, in our scientific journey. Okay. So this is something we're trying very hard to do, and by 2029, we hope to build some of the largest scale fault-tolerant quantum computers. Okay? And this is going to be a tremendous challenge for us as a civilization, a tremendous engineering challenge. Okay? And we've taken on many of these in the past, and this is something the team at IBM, but also all across the world, are very motivated to solve. Okay, so we're making progress. We're trying to make progress towards an error-corrected quantum computer, a large-scale error-corrected quantum computer. This is going to likely happen, by the end of the decade. What can one do in the meantime? What can one do if you didn't have error correction? Is there something we can do with existing devices? This is the question worth asking as well. So let's take a simple example of, say you had about 100 qubits, 100 quantum bits, and you wanted to apply about 10,000 instructions to these 100 qubits. That quantum circuit I showed you a picture of, maybe you wanted to apply 10,000 of those circuits, 10,000 operations in those circuits. And let's say that each of those operations had an accuracy of about 99.9%. So the probability of an error was just 0.1%. Now, if you multiply that number for each of those 10,000 operations, and you ask, well, how accurate is the final state that you prepare with that quantum circuit, that's going to be an incredibly lousy number. Okay? So this isn't very promising. This once again tells you that you need error correction long term, but let's still push forward and ask, is there still something one can do with this? Right? Okay, so I'm going to take you through an example of, say you had about 1,000 spins or 1,000 magnets all aligned in one direction, and let's say that one of these flip. Okay? So the kind of metric we calculated on the previous slide, if you asked, well, what is the overlap between these two states, it's going to be completely wrong. It's going to be 0. But instead, if you asked, well, what's the total magnetization of this system? What's the average magnetization of the system? The answer to that is only going to be wrong in the 3rd digit. Okay? So what this begins to give you some intuition for was that even though you introduced some errors, there were quantities that you could estimate which aren't too bad, which are fairly accurate. Okay? And so this is the game one can now play with the quantum circuits. That's perhaps the quantum circuit that you want to execute on your device. And then if that is sufficiently short depth, and what I mean by depth is basically the number of these blue operations, if that's not too deep and you don't accumulate too many errors, perhaps there are some quantities that you can measure at the end, which might not be completely wrong, even though the state you're preparing at the end gets quite corrupted. So this was basically something we tried to do in 2017. For a very simple molecule, just with 4 qubits, we tried to ask essentially the energy of dissociation for this molecule, right? What we discussed on one of the initial slides, right? This was just for 4 qubits for a molecule that we mapped called lithium hydride, okay? And so this is, because it's 4 qubits, the matrix that one has to diagonalize, that's very small. This is something one can trivially do, perhaps even on your phone. And that's why you know what the right answer is, right? And you can test, well, is the quantum computer producing the right answer? And it's actually producing the completely wrong answer. It's a horrendous result. If you ask any computational chemist if this is, if this kind of calculation is worth their time and effort, they'll probably get really mad at you, right? So even with such simplistic circuits, even at such a small scale, this was going to be a challenge. Okay, so this basically now led to what are called error mitigation techniques. And this was basically invented at IBM, but also simultaneously at the University of Oxford. And essentially the idea here is, with these techniques, is instead of encoding information in these larger networks of qubits, we're going to try and characterize the noise. We're going to conveniently try to manipulate the noise, and then hopefully we can undo this effect. Right? Now, when I'm saying this, maybe this doesn't sound that uncommon to some of the devices we use even these days, right? Like our noise-canceling headphones. We're manipulating the noise to try and create a less noisy environment, around our ears. A lot of our devices have some principles of noise cancellation. So that's the basic idea with these methods. And this is one of those techniques. It's called zero noise extrapolation. And the basic idea is you run some quantum circuit. In this case, I'll just ask you to make a leap of faith. And believe me when I tell you that the correct answer was supposed to be 1. Because of noise, when you actually ran it the first time, excuse me, the answer was away from 1. Okay, it was wrong by about 0.2, about 20%. Now, if you were able to characterize the noise on the device and very precisely amplify that noise, now by a factor of 1.2 and 1.6, you get further and further away from the correct answer. But now you can use these 3 different measurements to try and do an extrapolation, to try and extrapolate to what the answer could have been in the absence of noise. Okay? And that's what this fit does, and you actually get very close to the correct answer. Okay. So maybe there's a method, there's actually a way to perform something accurately, even though you have noise in the system. Okay? So we went back and looked at that 4-qubit example, that simulation of lithium hydride, a couple years later. And then, by measuring at these different noise strengths, by extrapolating to the zero noise limit, we were now much closer to the green curve. Okay. But this is very promising, but this is only on 4 qubits. This is something we could have done on a phone. So what does one now need, to have some utility to using a quantum computer? Well, 1, you need the number of qubits to get to a scale where you can't do the kind of brute force classical simulation I was referring to. You shouldn't be able to diagonalize. Otherwise, you would just use the classical computer for this, right? So you at least want this to be at a sufficiently large scale. And next, when you're at the scale where you don't know what the right answer is, you still need to be able to build trust in the quantum device, in the solutions the quantum device is providing for you. And this is very much similar to the games that classical computational scientists have been playing for decades, right? Computational scientists that use classical computers, right? So if we can build quantum computers at scales beyond brute force diagonalization, and we can begin to produce results that have some element of accuracy, some aspect of trust in those kinds of solutions, then we begin to have some usefulness to a quantum device, to a quantum processor. Okay? I apologize. I think we realized a little late that this slide didn't quite get transferred well, but essentially, I think it's sufficient for you to know that basically, even in 2023, we've built quantum processors at IBM that go up to over 1,000 qubits. Okay? So already at this 2020 device at about 65 qubits, you're already looking at a number of qubits where you can't store all of all of the parameters associated to describe the system on the world's most powerful supercomputers. You just run out of memory, okay? So we've basically already ticked off question number 1. And now for question number 2. Can the quantum computer produce trustworthy solutions? Okay? So for this, I basically want to, for the last part of my talk, I want to describe this quantum utility experiment that we worked on, right? First, this was on 127 qubits, well beyond what you can do with brute force classical simulation. And of course, this is a much more complex device than just the singular chip that I showed you with 2 levels, with 2 qubits. And this image, should give you a sense of how much we can benefit from all that we've learned with CMOS manufacturing techniques and all of that, and how all of that's now translating to build fairly complex processors with multi-chip wiring and so on for our next generation quantum devices. Okay. And so what was this experiment? The question we were asking was, we have a network of about 127 spins, and this is an interacting spin system, and we want to give the system a kick in terms of an external field. And we want to ask the question, how does the global magnetization, so if I think of this interacting spin system as one giant magnet, how does that magnetization of that magnet evolve in time? Okay? And this was an experiment that was led by Young-Suk Kim and Andrew Edens on my group. And basically, as they changed the parameter of this field, they tried to ask the question, how does this magnetization evolve? Okay? So what's being swept here is the angle of that field, right? So in the absence of the kind of error mitigation, you had the green points, and then with the zero noise extrapolation, you could bump up that curve to the blue points. But this was on 127 qubits. We didn't have access to what the right answer was straight out of the bat. So we approached Mike Zalotal's group at the University of California, Berkeley. Sajant Anand was one of the graduate students there. And we asked them to give this a shot, right? And so they tried the same game that one plays with classical simulation methods. They tried some of their approximations, right? And then basically what we saw here is, okay, for some parameter angles, there's very good agreement between the experiment and the magenta line, okay? But then later on, there is this decay. And all of our first reactions were that, okay, surely the quantum device is noisy. These are methods that have been studied for several years. Surely the methods must be correct. The classical methods must be correct, right? But then Sajant, was a persevering graduate student, and he stuck with this, and he noticed that, for this kind of circuit, there could be some other tricks that are very unique to this problem. Okay? And he said that no, actually, even though this problem is beyond what you can do with brute force diagonalization, there are additional tricks that I can play to actually get what the right answer should be. So let's try and do that comparison. And when he did that, he gets the gray line, and the experimental points from the quantum computer fall bang on top of that line. So this gave a lot of trust. A lot of trust that the device was noisy, it has lots of errors, it's on 127 qubits, and still you can produce solutions that are correct, that are accurate. So this was a big surprise to all of us, right? Now, this was because of certain aspects of the problem. The number of instructions weren't large enough, so we decided now to push the depth, which is basically the number of operations, from depth 15 to depth 60, where Sajant could now no longer play those tricks to get the exact result. And now we ran the experiment. We didn't know what the right answer was. And soon after, there were a number of groups from the classical simulation community that also tried to simulate this circuit. Okay? And this is all happening now in the absence of what the right answer is. Okay? And that's what this looks like. Right? There were a bunch of different groups all across the world, and you don't know what the right answer is, and you have that kind of spread. Which of these is correct? You just don't know. Right? What I haven't told you, or what I didn't tell you at the start, was one of those points were from the error-mitigated IBM quantum computer. Okay. And if I put labels on the remaining points, you can see that all the others were the classical simulation techniques. So now, even though you have quantum computers that are error-prone and noisy, you can now begin to play the game that computational scientists have been playing for decades with classical simulation techniques. It's because you can operate these devices at scales beyond what you can do with brute force, where only classical approximations can help you, and you can now begin to play the game of trust in your quantum methods, the game of trying to build confidence in the results that you get from these, and compare them to how other classical approximations perform. Okay? And that's why this paper was titled Evidence for the Utility of Quantum Computing Before One Has Fault Tolerance. Okay, cool. This is the final slide. I just wanted to give you some more perspective on what are the kind of things people are doing today with these systems. There isn't necessarily always a competition between quantum and classical. There are paradigms of computing which leverage quantum as a part of a high-performance computing routine on a classical computer. And it really blows my mind. You know, in 2017, when we did some of these chemistry experiments, you know, once again, you'll recognize those curves. Those were just on 6 qubits, going up to molecules as silly as beryllium hydride. And just last year, you know, folks from IBM in collaboration with Riken in Japan, you know, have basically figured out methods to simulate fairly complex molecules using up to 77 qubits. Complexes like Fe4S4 and a host of other molecules as well, where the solutions you can get now at the scale beyond what one can do with brute force classical computing begin to compare quite well with other classical approximation methods. So in a span of about 7 years, we've really seen new ways, new algorithms by which we can really expand the kind of molecular simulations one can do you know, with quantum computers, leveraging help from classical HPC as well. So this is a newer emerging area which I think has a lot of promise. And with that, yeah, just for my take-home messages, noisy quantum computers today can perform accurate computations at non-trivial scales, at scales beyond what one can do brute force. Extending this to dramatically larger numbers of operations for the circuits to get much longer. Eventually, one will need quantum error correction. This is going to be one of the hardest challenges we have in science, and this is something a lot of people across the world are actively working towards. And there is a new emerging paradigm where one can club in a quantum computer with classical high-performance computing and do the kind of things that we thought were decades away. And I think this is going to be a very promising path to near-term quantum advantage. Okay. Yeah, a lot of the work I shared, you know, clearly is not, you know, possible with a small number of people. It really takes a village, and you know, for that I must acknowledge the contributions from the entire IBM quantum team and our collaborators and so on. And thank you for your attention.
Thank you, Dr. Kandala, for the insightful talk. So now we will open the floor to questions from audience. As my colleague collecting the questions, maybe I will start with a question of my own. Yeah. So you mentioned the software approach to do the quantum error correction. So I wonder if it's universal for all the algorithms, or for specific question, you need to train a certain model for this kind of error correction regime.
Yes, I see. So I think you're referring to the error mitigation.
Yeah.
Right, exactly. So if I have to rephrase the question, the question is, depending on the application or depending on the circuit that one wants to run, does one need to do something differently to be able to address that kind of application, right? Yeah. So very often, the first part of these error mitigation protocols that I mentioned, which was characterizing the noise, that can be quite dependent on the context of the circuit, on the context of the application, right? So depending on the noise that you are in, or depending on the noise that that your device sees, you might have to recharacterize it. And so this is something that's fairly standard. I mean, even with the analogy of the noise cancelling headphones that I was talking about, right? Depending on where you are, the kind of room you're in, are you in an airplane, are you in a room like this, the impact or how well that performs can change. So yes, that's a great question, and the short answer is you have to recharacterize the noise depending on the kind of circuit you're trying to run.
Yeah, thank you. Maybe another question about how will this technique impact our daily life? Like, is there any algorithm that is less sensitive to the quantum noise so that we can do some really meaningful calculation and have some daily application?
Yeah, so noise is actually something very interesting. So typically, if there are quantities that are very insensitive to noise, then what that likely will also translate is that there will likely be a classical simulation that one can also do by introducing that kind of noise in classical simulation. So then one can raise the question, well, what's the point of doing this on a quantum computer? Because you could have just done that same simulation on a classical device, introducing that noise artificially. So there's a fine balance where you want the sensitivity to noise to be just the right amount, so you can do tasks on quantum devices that you can't on classical. But this is an area of intense research. Are there problems that one can do that affect our day-to-day today? The answer is no. But I think should that prevent someone from asking the question? Absolutely not. I think it's quite amazing how quickly things have moved over the last few years, and I think there should be people thinking about this.
Thank you. Now I'll read the question from the audience. So the first question is about AI. So will the AI be able to help the quantum computing, will quantum computing help to solve the computational power problem for AI?
Yeah. Okay. This is a question we get very often. Yes. So can AI help quantum computing? I think so, very much, and we already see examples of these. Quantum systems inherently are very challenging to calibrate and deal with and get operational. And there perhaps is a lot of automation one can actually benefit from using things like AI to actually deploy a quantum computer much faster than before. I spoke about noise in these processors and how noise impacts the accuracy, more the number of operations, more the number of gates in your quantum circuit. You can have more noise that you have to deal with, and the answer gets corrupted more. But you can use techniques in AI to actually reduce that depth, to reduce the number of operations in intelligent ways, so that you actually reduce your sensitivity to errors. So that's one way in which AI is certainly helping quantum computers. How can quantum computers now help with AI? Often problems in AI involve mapping to higher dimensional spaces, right? So that very intuitively can give you a sense of, we spoke of operations in quantum computing being rotations in a higher dimensional space. So that naturally feels like one area where one could leverage some of those kinds of techniques. This was also one of the papers we worked on a few years ago to do binary classification tasks with a quantum computer. But this is all preliminary, I think, at this point. There isn't like a large-scale advance yet, but this is very hot, active research.
Yeah, thank you. Now I have a question. Ask for your comment on Microsoft's recent result. So for normal audience information, Microsoft just say they got some quantum computing chip based on their Majorana 0 mode, which is very, the community of physics are very dubious about their result. So now let's listen to Dr. Kandala's opinion.
So I am an employee of IBM, which is a competitor. So you can take what you can from that disclaimer. So you can take my comments from a pinch of salt. But what I also am is a graduate student in Professor Samart's group, formerly. And what we worked on together were on a class of materials called topological insulators. Okay? So what topology can do with for materials is a topic that's very dear to me. So even though I'm an IBM employee, I really want them to succeed. Okay? I really, really want them to succeed. Because they're approaching this problem with a different direction using topological qubits. And I would love to see that in imperfect solid-state systems, you can have these beautiful ideas of topology and protected information lead to more stable, more fault-tolerant quantum computers. I would love to see that happen. Do we have compelling evidence yet that we're there? I think no. I think a lot of the commentary you're probably seeing in social media or news articles these days seems to be because of some kind of discrepancy between what this paper that was published in a high-impact journal in Nature, what the conclusions of that paper were, and there was a discrepancy between that and the press releases. And I think there will be more announcements coming up, is what I hear. For the condensed matter community, we have this conference in LA called March Meeting, where about 15,000 of us gather together and discuss the latest and greatest in condensed matter physics. So we might hear more then, but based on everything I know from the paper, there isn't yet a topological qubit.
Yeah.
But there might be something more in the works.
Yeah, thank you. There's a question about the problems now are solved by different quantum computing companies like IBM. You have this quantum chemistry result, and Google and other companies, they're also targeting different problems. Can you just distinguish those problems and what's the point of for these different companies solving different problems and how to compare them?
Yeah. I wouldn't quite say that different companies are targeting different problems. I think there are companies that are producing different kinds of quantum computers, and they all have their different pros and cons. And then eventually, and you're beginning to see some of this, you'll have a user who is kind of disconnected from the details of the quantum device, much like an app developer for a smartphone, right? They don't quite know how the smartphone was built or what technology went inside the smartphone, but still have the ability to program it and write new apps, right? So there are a whole bunch of application scientists, people from chemistry, people from AI, ML, who are very interested in asking what can quantum computers do for questions that are problems they deal with on a day-to-day basis, and they're basically interested in trying these problems on different platforms, different systems. And that's why, for instance, at IBM, there's a huge emphasis on trying to deploy these systems, on trying to have these systems not just in a lab for a bunch of experimentalists to fiddle around with, but also for scientists anywhere in the world with a connection to the internet to be able to run and try out and build the software infrastructure to support that as well.
Yeah, thank you. Here's a question about, basically, as I summarized, maybe the quality and the quantity. You may have many qubits, but they are noisy, but compare with high-quality logical qubits, maybe. So is there a trade-off between those two?
So the question is as you try and build larger and larger networks of qubits, is there necessarily a trade-off in the quality, in the probability of errors? In recent times, I would say no. Certainly, a few years ago, that was the case. But right now, very often the kind of best metrics that we report for the 2-qubit error rates, they often are on the largest devices. There are some aspects which get more complicated. That's certainly true. But basically, the idea of quantum error correction is if you can scale, keeping the error rate sufficiently below some threshold, you can eventually encode this information into a larger number of qubits so that the logical error at the end will be lower than what you had before. So that's the idea.
Yes. There's a question about, so how close are we to having a quantum computer that can solve the decryption problem? Maybe it means like more about internet security or?
Yeah. Right. So this is probably a question that's of most interest to our intelligence agencies across the world, and perhaps our banks as well. So this has also been one of the big motivations for understanding what quantum computers can do and not. There was an algorithm that I think came out in 1995 called Shor's factoring algorithm that showed that you can more efficiently factor a very large number using a quantum device than is possible on a classical device, on a classical computer. We're quite far away from that. Let me say that. Okay, I shouldn't. That said, there can be dramatic breakthroughs in algorithms and overheads and understanding. There actually was one last year, after about 30 years. That was probably the only breakthrough on Shor's factoring algorithm that actually reduces the overhead dramatically. But addressing those, I think, will basically be the post-2029 landscape when we need an error-corrected quantum computer for sure. But it's not happening this year.
Yeah, thank you. And there is a question about the access to quantum computer. Like, is there a way for researcher or just normal people to have a taste of the quantum computer? I think IBM may help that.
Yeah, absolutely. So in fact, when we first began to put out quantum processors on the cloud, these were essentially free devices up to 5 qubits. I think we also had a 16-qubit device later, a couple of years later, that was freely accessible. And so a lot of people have run, a huge number. I think I probably lost count, but if I were to guess, probably at least 5,000 papers on the archive from the broad community, from the academic community, leveraging just free use of these quantum computers. What has changed more recently, though, is I think for the smaller scale tests of getting familiar, it's really a matter of changing one line of code, where you go between a quantum simulator that you can run on a classical machine versus actually running on a quantum processor. So at this point in time, I think it's quite convenient to even just play with a small scale classical simulator of the quantum circuit if you were interested in. And for instance, at IBM, we've really shut down on the small scale devices, particularly after this result, because what that's forced the community to do is to really push much harder at the larger scale problems, right? And so there's almost been a phase transition in our average qubit use, going from 2 years ago to last year, where the average qubit use by people used to be on the order of 10 qubits. Now it's at about 115 qubits, which means that for users trying to use these systems, on average, every circuit they're running, on average, is about 115 qubits, which is well beyond that scale of brute force computation. So what this means is now that there's so many more people actually trying to do computations that one couldn't do with brute force classical simulation. So that's where things have gone in terms of hardware access, but I think for a lot of people trying to play, there are lots of tools available for free.
Yeah. Oh, that's very impressive. So another question is about, do you think there are other methods of noise reduction that may be explored, such as a placement of the computer in space? In this question. Yeah.
So I won't comment on the space bit, but certainly a lot of people are trying to put quantum computers deep under the ground. So what has been seen by some groups is that these quantum bits can be quite sensitive to cosmic rays, and that can cause dramatic changes in the performance in the lifetime of these qubits. So one test that they've tried to do is to take these entire big fridges and the quantum processors in it and place it several feet under the ground. These are experiments that are being done at Fermilab and other places, leveraging facilities that some of the US national labs have already. So there are all kinds of things like this people are trying out and seeing if it helps.
Yeah. I think I'm running out of questions. So let's thank the speaker today again.
Thank you so much.
Yes,
Is it on?
yeah, it's on.
Hi. Good afternoon. Alexander Seshaslavkovich. I'm professor of statistics and currently Associate Dean for Research in the Eberly College of Science. Many thanks again for joining us today, and please just give me a few minutes. Abhinav, I would like to thank you on behalf of everyone here today and online and of the entire Eberly College of Science community for your very educational and engaging lecture. It's great to have you back at Penn State. It's terrific to learn about your amazing successes over the past 10 years. Congratulations. And to learn, as I said, or hear about your experience and visions on deployment and application of quantum computers. I would also like to thank Nitin for his opening remarks and for highlighting quantum science, the importance of quantum science, as many of our outstanding researchers at Penn State and the Eberly College of Science are looking to lead solving the next generation of quantum challenges. A huge thanks go to amazing staff from the Eberly College of Science Communications Office and the Associate Dean for Research Office for organizing this lecture series. Today with us we have Heather Robbins, Sam Schultz, and Stephen Smith. Thank you again. Very important. Many thanks to Peng Du and Tommy Chen, who are graduate student in physics, for helping moderate today's Q&A. I do have two important announcements for the remaining two lectures of the series. First, next Saturday, March 1st, we will be in a different location. We will see you at 001 Chemical and Biomedical Engineering Building. It's nearby. And please join us to hear Professor Jun Zhu talk about building a quantum information highway. Right, Jun? You want to wave to everybody? Great. As you know, last week's talk had to be canceled due to weather conditions. It's now been rescheduled. It will be after university spring break on Saturday, March 22nd, start time 2 p.m. in this location. And please make sure to join us for that. Professor Marcus Rigol, who is also here in the audience, okay, we'll be discussing a tale of two gases, chemical and quantum, classical and quantum, and as promised, there will be live demonstrations, so you definitely don't want to miss that one, okay? And of course, I don't want to forget, please use the QR code and complete the survey. That helps us, as you know, as you heard before, to plan on the next lecture series and engage better with you. Please leave your email with us if you would like to get notices of the upcoming lectures. And finally, a lot of this information that I just shared with you, you can find any updates on the upcoming lectures and definitely on the next two lectures at science.psu.edu/frontiers. And again, thank you for coming today. We hope to see you next week and have a great weekend. Thanks a lot.